In order to see how you might use dimensionless analysis, we're going to go back and study a problem we've studied with dimensional analysis already, which is the steady, fully developed flow between two plates. So we've got the plates here, got X and Y coordinates, Y going across the channel. Plates are long in and out of the paper, so there's no interesting stuff happening in the Z direction. And we've got a gap height between the two plates of H, and so the flow is fully developed. So we know it's steady flow, so that means d by dt is going to be 0 for all things, no time dependence of any kind. And for fully developed flow, what that means, as we've seen before, is that there are no x changes in velocity. So the x direction velocity is no longer changing. It's taken on what we now know as a parabolic profile, and that's just staying the same. So we're going to go ahead and solve it as if we didn't know the answer already, but we're going to solve it using our dimensionless equations. So let's start with our dimensionless continuity equation. So we have du tilde dx tilde plus dv tilde dy tilde is equal to 0. Well, d by du dx is going to be 0 because it's fully developed flow, and so that means that dv tilde dy tilde is equal to 0. Well, do we know? That means if we know v tilde anywhere in the y dimension, we know v tilde everywhere in the y dimension. V tilde is just v over u infinity, some characteristic velocity that we haven't really defined yet, and we're not going to define until a little bit later. But we know that it's going to go to 0 at the walls. So v tilde is 0 at the walls. The y dimension, of course, is just y over some length scale. So y tilde is equal to y over L. So the y direction is the same as the y tilde direction. And so we can say that if v is 0 anywhere, v is 0 everywhere. We know v is 0 at the walls. V tilde equals 0 at the walls. So v tilde equals 0 everywhere. Same exact thing we did when we solved this dimensionally. All right, so that's going to allow us to really simplify some things. Let's go ahead and do that. So if we take a look at our Navier-Stokes equations, our momentum equations, we're really just going to look at the x momentum equation. The y momentum equation has all v's in it, and we just said v is 0 everywhere. So there's nothing going on there. And we also said that d by dt is 0. So I'll write that again. With that, d by dt 0 is going to leads to the fact that d by d tau is also 0 because it's just d by dt times a constant. So we're going to have d by d tau tilde is equal to 0. So the first term is going to go away. D by d tau tilde plus u du dx tilde plus v du dy tilde is equal to minus dp tilde dx tilde plus 1 over the Reynolds number based on h, our characteristic length scale we're going to choose as h, d squared u tilde dx tilde squared plus d squared u tilde dy tilde squared. So I say we chose h as the characteristic length scale because really it's the only length in the problem. We don't know how long the plates are. It's not specified how long the channel is. Even if that were specified, it's not a very interesting direction because nothing's happening there. All the action is happening in the y dimension, and the characteristic length in that dimension is h. So h is the natural and correct choice for this particular problem. So we're going to choose that as our characteristic length, which affects our Reynolds number because it has an h there in it. All right, so now we're going to get rid of terms that are 0. So that's 0 because of the no time dependence. This is 0 because there's no velocity gradient at x. This is 0 because there's no v velocity. And this is 0 because there's no velocity dependence in x either. So we're only left with two terms. So we have the dp dx can come over to the left-hand side with its dimensionless terms here, and that's going to equal 1 over the Reynolds number based on h of d squared u tilde dy tilde squared. So there's our equation. This, of course, just as was true for the dimensional case, that's only a function of the x variable, and this is only a function of the y variable. So we know that velocities don't depend on x in this problem, and the pressure only depends on x. So, we can and we know it's not dependent on y because the y momentum equation tells us that. So if you want a refresher on why that is, all the v terms go away and you get the p dy is 0. So there's no pressure change in the y dimension, there's only pressure change in the x dimension. So that means these both have to be equal to a constant. And so these are a constant and they're g, but I'm gonna put a tilde on it because these are dimensionless now, right? There's no dimensions in these terms, so there can't be dimensions. The g that we used before was dp dx, and of course that has dimensions. It's pascals per meter. So this is not. This has no dimensions at all. So I'm just putting that tilde to remind us that that is a dimensionless g. So now I'm going to go ahead and solve, this bit right here. G is still constant because it has to be constant for these two to be equal to each other and remain equal. So we have the G is a constant, and I'm going to integrate both sides. So I have 1 over the Reynolds number based on H, d squared u tilde dy tilde squared is equal to G tilde. And now I will integrate that. So I'll just can put the Reynolds number on the other side. I can take the derivative of du tilde dy tilde is equal to g tilde Reynolds number based on h times dy, and that I can integrate on both sides. The integral, of course, of du dy, d by du dy is, if d of du dy is just du dy, and the right-hand side, of course, is just going to give me y plus a constant integration. So on the left-hand side, I have du tilde dy tilde is equal to g tilde Reynolds number based on h times y plus some constant I'm going to call c1. I can easily integrate that again. I end up with du on the left. I end up with g tilde rehy squared plus, sorry, not y squared yet, just y, plus c1 times dy. And now I integrate it to get my y squared. So I have u tilde is equal to g r Reynolds number based on h y squared over 2 plus c1y plus some other constant integration c2. All right, now I have to apply some boundary conditions. That's my general solution. And my boundary conditions are, first one is du tilde dy tilde is equal to 0 at y equals 0. Now remember, I didn't really highlight this, but as I drew it, that's the center of the channel. So in the center of the channel, the symmetry condition is that the gradient of the velocity has to go to 0 in the y direction. So du dy has to be 0 at the center, which is y equals 0. So I'm going to use this equation that we had already. Du dy equals this. If I take the derivative of this, I get that. So du dy, I know, is equal to g tilde rehy plus c1. At y equals 0, this is supposed to be 0. So 0 equals 0 plus c1. That therefore leads to c1 equaling 0. Now I update my general solution. So if I plug in c1 equals 0 to that, and I get that my new solution is u tilde equals g Reynolds number based on h y squared over 2 plus c2. No c1 term. My second boundary condition is that, if I look at this, my velocity has to go to 0 on the wall. So that's at h over 2. But I have to translate that into y tilde terms, right? So this is a y tilde. I should have been carefully keeping my y tildes here. Sorry about that. These are all y tildes. Go back and put y tildes everywhere. Tilde, tilde, tilde. That was kind of a goofy mistake. Yeah, we had y tilde, y tilde, y tilde, y tilde. So y tilde, the question is, what is y tilde at y equals h over 2? Y equals h over 2. Y tilde equals y over h. Therefore, y tilde equals h over 2 over h equals 1/2. So y equals 1/2 at the wall. So y tilde equals 1/2 at the wall. So that's my boundary condition, that u equals 0 at y tilde equals 1/2. All right, so there's my boundary condition, which I'm going to use to put into this equation. So I put in u tilde equals g rehy tilde squared over 2 plus c2, and I'm going to apply this boundary condition. So I put in 0 on the left for the value, I put in y equals 1/2 there. So I get GREH is equal to 1/2 squared over 2 plus C2. And of course, that means that C2 is equal to negative GREH over 8. So I plug that into my equation, back into my general solution, which is here. So I plug this C2 into that, and I get that the U tilde is equal to GREH y tilde squared over 2 minus GREH over 8. Well, I can definitely improve on the looks of that. So my U tilde is going to be GREH, which appears in both terms. And then it's going to be 4y tilde squared minus 1. In fact, that will be negative in the entire domain. It will be 0 or negative because y only goes up to dh over 2. It only goes to 1/2. So 1/2 times a fourth gives you 0, as it should at the boundaries. But I would like to make it look a little more obvious what's happening here. So I'm going to write it as GREH times 1 minus 4y tilde squared. So remember, if the pressure gradient, and this should be G tilde, oh Grace, G tilde, G tilde, G tilde, G tilde is all the way back, G tilde, G tilde. So our pressure gradient, if it's negative, that will give us a positive u velocity. If our pressure gradient is positive, then that will give us a negative velocity. So that's our final solution for the velocity profile minus g. Oops, what did I do with my 8? Divided by 8. Divided by 8. Where'd that? I want to make sure you see where that came from. Oh yeah, it was here. This is supposed to be by 8. I divided everything. I pulled the 8 out, and that makes this into a 4. And that makes, of course, this into just a 1. So that's where that was supposed to come from. So yeah, sorry about that. So we pull that out, get this. This is our solution. And remembering that for G is negative, that gives us a negative pressure gradient, which actually drives positive flow velocity.